9.3 Similar right triangles. Essential question: how are altitudes and geometric means of right triangles related? Let's first talk about the word mean. When you sum up a set of numbers and divide by the number of numbers, that is called a mean, an arithmetic mean. What we want to talk about today is geometric mean. Geometric mean of two positive numbers, a and b, is a positive number x that satisfies this proportion. Notice that the two numbers along the diagonal have to be the same. This is going to lead to a product, which is going to create a square, and to get the geometric mean, you're going to have to take the square root. So geometric mean has to do with multiplying numbers and then taking the square root instead of adding numbers and then dividing. Let's go ahead and do this problem. So we would like to find the geometric mean. So I'm going to call this x and x. Okay, a geometric mean is always the same number along the diagonal, and this is going to be 24 and 48. I'm going to cross multiply. 24 times 48 is equal to x squared. Take the square root of both sides. When I take the square root of both sides, I'm going to rewrite 24. 24 I know is 8 times 3. I'm going to write 8 as 2 times 2 times 3. I know that 48 is 16 times 3, so I'm going to write 2 times 2 times 2 times 2. That's the 16 times the 3. Now to simplify a square root, remember that you take them out in pairs. And then we have a pair here. So I'm going to have a 2 times 2 times 2 times 3, and then I'll have one factor of 2 there. So this is 8 times 3, or 24 root 2, and that's the simplified version of that square root. Okay, now your turn to try. And here are the answers. Again, setting up the proportion and then multiplying across and then trying to simplify the square root. Right triangle similarity statement. We are going to have a right triangle and we are going to draw an altitude to the hypotenuse, which is what's happening here. When we do that, we create three right triangles, the original and two smaller ones. And what this theorem says is that all three of those triangles are similar to each other. Let's look in more detail. What's going to happen is this medium triangle can split off over here, this little triangle can split off over here, and we can rotate and reflect so that the right angle's right here at this corner and the red angle's up at the top. We can take the big triangle, rotate it so that the right angle's right here in the left-hand corner and the red angle's at the top, and do the same over here. So you can see that all three triangles are similar by angle-angle similarity. I'm going to do the first problem and be ready to do the second one. I want to identify the similar triangles. So I know there's a big triangle, a medium triangle, and a small triangle. So I'm going to start with the big triangle. QSR is similar to triangle. Now I'm going to be looking at the medium triangle, which is this one. I'm going to put polka dots here so you can see it. And I want you to notice that angle R is the same as angle R for the big triangle. So I'm going to put an R right here in the same position. I know that angle S is the right angle, and for this triangle, angle T is the right angle. And there's only one letter left, which is S. Now I'm going to go to the small triangle. I'm going to put stripes here to have myself identify that. I see angle Q is angle Q for the small triangle and also for the big triangle. So I'm going to put Q right here in the same position as the big triangle. Now again, the right angle for this small triangle is T, and I'm putting all right angles in the middle. There's only one letter left, and that is S. And that's how you set up all the letter order for the three triangles. Give it a try for number 2. And here is the answer. Let's look back on this situation again, this right triangle with an altitude drawn, which creates the big triangle, medium, and small. I repositioned them so that they're all aligning and their positions are the same. I'm going to take this two small ones and write the similarity statement. Now I'm going to do the sides in proportion, AD to CD, DC to CB. Now when I do this, I notice something very interesting. I notice that I get a geometric mean. Remember the geometric mean, you get one when you have the same thing across the diagonal. It could be X or it could be DC. Now, instead of memorizing letters, I'd like you to memorize what it represents in words. And DC is this thing right here, which represents an altitude. So this is going to be an altitude, an altitude. AD is this, which is part of the hypotenuse of the original triangle, and DB is the other part of the hypotenuse. So there's a proportion happening here. Let's look at the same situation, but this time we're going to compare the big triangle with the medium triangle. And again, I've set up my similarity statement and I write my extended proportion. What's very interesting is I see a geometric mean happening again. Two of the same thing along the diagonal. What I'm going to do is look for its representation in words. So here's AC, and AC represents a leg. So the leg is the geometric mean. It's along the same diagonal between AD, and AD seems to be part of the hypotenuse. And there's two parts, this one and this one. I'm going to call this a part of the hypotenuse adjacent to the leg. And then AB up here is the hypotenuse. So we have another proportion happening. It's called a geometric mean. Now this is the theorem. And the words tell us how to write this out in words. It says the length of the altitude, this thing right here, is the geometric mean. So I'm going to put altitude, altitude along the same diagonal between of the lengths of the two segments of the hypotenuse. So I'm going to write part of the hypotenuse, other part of the hypotenuse. So instead of memorizing the letters, memorize the words and you'll be fine. Now the other theorem that we just looked at was the length of the leg of a right triangle. So is the geometric mean. So I'm going to put the leg along a diagonal. It doesn't matter whether it's this diagonal or this one. And it's the geometric mean of the hypotenuse of the big triangle and the segment of the hypotenuse adjacent to the leg. So part of the hypotenuse adjacent to the leg. So these are the two theorems we need to utilize to find unknowns. I'm going to do this problem. I can see already that this is an altitude, so I'm going to use the altitude theorem. It's called the geometric mean altitude theorem. Altitude, altitude, part of the hypotenuse, other part of the hypotenuse. So I'm going to put x and x here, and then 6 and 3. And if you mixed it up and said 3 and 6, you get the same thing. So we get x squared equals 6 times 3. So x squared is equal to 2 times 3 times 3. I'm going to take the square root of both sides. So I'm going to get x is equal to, I see a pair here, and then I'll be able to take that out of the square root. So the answer is 3 root 2. In this particular problem, I don't have the altitude, I have a leg. So I'm going to use the other theorem, which is the geometric mean leg theorem. So I'm going to put y here and y here, because the leg is a geometric mean between the whole hypotenuse, which is 7, and the part of the hypotenuse adjacent to the leg. So this is going to be 14 is equal to y squared, y is equal to root 14, and we can't simplify root 14. So I'm going to go back again to this page. These are the two theorems that you need to be able to use. Okay, your turn. And here are the answers. So again, x was using an altitude, where this x was not an altitude but a leg, so I have to use the leg theorem to get these answers. Now I'm going to take a look at this problem. I'm going to walk you through. I'm trying to find an altitude, but unfortunately I don't have the parts here, so I can't use the geometric mean altitude theorem. I'm going to have to use the leg one. and I'm going to be using this leg right here. So I have the 4 and 4, and here's the whole hypotenuse, and then I'm going to call y the part of the hypotenuse adjacent to this leg. I'm going to cross multiply, and I'm going to get a value for the y, and that value will be 3.2. Now once I do that, I can now use the Pythagorean theorem because I have two sides of a right triangle, which I'm going to do right here, and I can get an approximate answer to the tens place of 2.4. See what you can do for problem 4. And here is the answer. Let's take a look at this problem. We're trying to find W, and the first thing you need to understand is which theorem are you going to use. Are you going to use the geometric mean altitude theorem or the geometric mean leg theorem? And you can see that 8.5 really is an altitude, so you're going to want to use the altitude theorem, which the altitude is the geometric mean between the part of the hypotenuse and the other part of the hypotenuse. On the next screen, you're going to see that I've substituted the numbers, and I cross multiply and find my answer. Last thing we're going to do is we're going to revisit the Pythagorean theorem using this brand new theorem that we're looking at. I'm going to go ahead and start the first one, that is the given, and then we're going to draw this altitude to the hypotenuse, which creates this part F, this part E, and this part C. Now I'm going to use the leg geometric mean, the geometric mean leg theorem. So this is the leg, this is the leg, this is the hypotenuse, part of the hypotenuse adjacent to the leg. And that's what I'm using here, right here and right here. So I'm going to write out the geometric mean leg theorem. Now, to make things a little easier, instead of writing the proportion, we're going to use the cross multiply version. Cross multiply version, cross multiply version. And we can call it the geometric mean leg theorem. Okay, our next step is we're going to take this right here and we're going to add the same thing to both sides. We're going to add b squared to this side and add b squared to this side. So this is going to be an a squared, and this is the addition property of equality. All right, now what I'm going to do is I'm going to substitute. So I'm going to take this b squared out, and I have a replacement for b squared. And so this is going to be called substitution. So this has been substituted. And now I'm going to factor out a c, which is distributive. So it's the opposite direction. Now let's take a look at what E plus F equals. E plus F is little plus little equals big. So in E plus F is equal to C, which is the segment addition postulate. Now I'm going to replace this, and I'm going to replace it with C. So this is going to be called substitution. And if you multiply this, you're going to get c squared is equal to a squared plus b squared, which is what we wanted to do. We wanted to prove the Pythagorean theorem.